Let us now discuss Heisenberg uncertainty principle, and it's called uncertainty because there is some non-surety. It just means not sure. So the scientists here came up with this principle of uncertainty where we cannot determine the position of electron at the same time determine its momentum. Now, what is momentum? Think of this example. If you have a feather of a chicken, and you drop it down, is it going to hit the floor hard? No. If it's dropping down at a given velocity is speed in a given direction. If it's going to drop down at a given velocity, it's not going to hit hard the floor. Now you take a weight from the gym, maybe a 3-pound weight, and you release it from top, let it hit the floor. Is it going to hit the floor hard? Yes. That tendency of hardness to stop, because the weight is hitting the floor hard because it's resisting being stopped. That hardness to stop is what we call momentum. So heavier objects usually have high momentum at the same velocity compared to lighter objects. That's what momentum is. Now you cannot determine the position and the momentum of an electron at the same time. It's one or the other. That is Heisenberg uncertainty principle. So now let's dig in after explaining the title. Electrons behave like waves. They are extremely light and small. We know the duality nature of electrons. We talked about that using de Broglie's finding, where he postulated and confirmed that electrons have both particle and wave nature. Their wave-like nature makes it impossible to know both their position and momentum precisely. A scientist called Werner Heisenberg formulated the uncertainty principle to express this quantum limitation, which is very, 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 very complex in details. The more precisely we know one quantity, position or momentum, the less precisely we're going to know the other. So you cannot tell where the electron is precisely found in the structure of an atom. So if this is an atom, that's the nucleus. So you cannot precisely pinpoint and say, hey, electron is there, or oh, electron is there. No. If you do that, then you'll not determine its momentum. Yet we know that electrons are always moving around the nucleus. Now, on the other hand, if you could find the momentum is usually just mass times velocity. Okay, if you can determine the momentum, then you cannot determine the position. So the more precisely you know one of these, either position or momentum, the less precisely we know the other. And after some calculations and math put together, this is the formula that was found. Delta x times delta p is greater than or equal to Planck's constant h over 4 pi, where delta x is a value or a quantity describing, this describes the position of an electron. Okay, and delta p is just mass times velocity, and that one describes the momentum of an electron. Okay, so now look at the equation very carefully. Look at the equation very carefully. So it says delta x times delta p, where delta is change, is greater than or equal to Planck's constant h over 4 pi. Pi, I think you can just use the pi of the circle. So what this is saying is that if delta x is so large, then delta P, the momentum is going to be so small. If delta P is so large, then delta X is going to be so small, because you're keeping this as a constant. Pi is a constant, 4 is a constant, Planck's constant, H is a constant. So if one increases, it will greatly decrease the other one. So if delta X is increasing, delta P will greatly decrease, and the opposite holds. So you cannot precisely determine the position of an electron at the same time determine its momentum, delta P, which is the same as mv, the momentum. Okay, so I've broken down the equation and explained what it is. According to Schrodinger findings, he found this equation where delta X describes the position, like I said before, and delta P, that's the momentum, is just equivalent to mv, or specifically we can say mass times change in velocity. Okay, so one can only be determined at a time. You cannot determine both of them at the same time in regards to the electron. So again, delta X is change in X, is uncertainty in position, and it's usually in meters. Delta P is uncertainty in momentum, usually in kg, meters per second, because you're looking at mass multiplied by change in velocity. SI unit for mass, I believe, is kg. For velocities is meters per second. That's where this came from. H is just Planck's constant as we know it, 6.626 times 10 to the power minus 34. And then pi is the pi we know as found in the calculator in regards to the circle. So h over 4 pi itself is going to be a constant. If you plug in the number of Planck's constant and plug in the value of pi, multiply, you should get a value that looks like this, and all that is a constant. Now if all this is a constant, so if this goes up, way up, this is gonna go way down, and vice versa. If the delta X goes way down, delta P is gonna go way up, and vice versa. So you cannot determine the position of an electron and its momentum at the same time. So let's look at a calculation involving Heisenberg uncertainty principle, which defines the uncertainty of finding an electron in an atom at the same time determining its momentum. It's one or the other. So given delta X, which is the uncertainty in position, can we find delta P, which is uncertainty in momentum, if we are given the uncertainty in position, delta X? So we know the Heisenberg uncertainty formula, which is uncertainty in position, delta X, times the uncertainty in momentum, delta P, is greater than or equal to h over 4 pi. Since we are looking for uncertainty in momentum of this electron in an atom of an element, so we are going to divide both sides by delta X. All this is going to be divided by delta X, and that means that here delta X will cancel, so we are left with delta P is greater than or equal to h over 4 pi over delta X. You can pretend it's delta X over 1, and this can also be written as h 4 pi times 1 over delta X. Just changing the division to a multiplication will convert this to its inverse, and therefore delta P is greater than or equal to h over 4 pi times delta X. This formula you are seeing here, that's delta X. This formula you're seeing there is this one. So now all that is left for us to do is to plug in the numbers. Our h is a Planck's constant, If you multiply this part as 4 times 3.14, just use the second shift on your calculator and multiply by 1.0 times 10 to the power negative 9 meters, it's gonna give you this value right here. You divide these two, there's a division sign here, this division sign, this is a Planck's constant h, divide by the answer you got from here. The uncertainty in momentum of this electron in the atom is 5.27 times 10 to the power negative 26 kilograms meters per second. You may be wondering how this SI unit was found in our answer. Remember that we got this formula: uncertainty in momentum is equal to or greater than Planck's constant divided by 4 pi delta x. Now the SI unit for Planck's constant h is joules second. So delta P is greater than or equal to joules seconds over 4, and pi does not have SI unit, but the uncertainty in position of the electron is in meters. I, however, know that 1 joule is equivalent to 1 kilogram meter squared over second squared. So where the J is, I'm going to put all this. So this will in turn be delta P, uncertainty in momentum of the electron will be equal to or greater than kilogram times m, that's meter squared, and then times the S, divided by S squared, and then all this is going to be divided by the SI unit of delta X, which is an m. This way, we are able to cancel out the S and the S, the M and the M. We are left with this combination of SI units, which is what you see right there. So in chemistry, you always have to justify physics, you have to justify SI units, and that's how that is found. Let us look at another example. Example 2. This time you are given the uncertainty in momentum. You need to find the uncertainty in position of the electron in an atom of an element. So you are given uncertainty in momentum to be equal to 1.0 times 10 to the power minus 24 kilograms meters per second. Find the uncertainty in position of the electron in the atom. Now remember what we defined uncertainty of momentum to be. It's simply mass times change in velocity. We know that the SI unit of velocity is actually meters per second, and that of mass is kg. You multiply these two together, those will be the SI units corresponding to uncertainty in momentum of an electron in an atom of an element. So we know Heisenberg equation to be uncertainty in position of an electron times the uncertainty of its momentum is greater than or equal to Planck's constant divided by 4 pi. So we are asked to find uncertainty in position delta x. So I'm going to divide through by uncertainty in momentum on both sides. And doing so, this and this will cancel. Delta P will cancel. And on the right, this is the same as delta P over 1. I can rewrite this expression as h over 4 pi times 1 over delta P. So we are dividing here. So if I do the inverse of this part, I can multiply. Instead of dividing, I can multiply by 1 over delta P. And therefore my delta x that survived on the left will be greater than or equal to h over 4 pi delta P. So once you determine this formula, which is this, all you need to do now is to plug in the numbers. Okay, so we know what Planck's constant is. It's 6.626 times 10 to the power minus 34. Now this part, if you multiply it through, multiply 4 times pi times uncertainty in momentum 1.0 times 10 to the power minus 24. kilograms meters per second, you're going to get this number. Now, if you multiply these two together, if you multiply Planck's constant and the value you got here, you're going to get the final answer of uncertainty in position delta x as 5.27 times 10 to the power negative 11 meters. Let's see how the meters stand, yet we have other SI units. Okay, we have to account for the SI units. So bring this equation down here. So delta x is greater than or equal to, the SI unit of Planck's constant is joules seconds. 4 and pi don't have SI units, but delta P, uncertainty in momentum, has the SI units kilograms meters per second. Now we know that 1 joule is equivalent to 1 kilogram meter squared per second squared. So where the J is, those units is what I'm going to put there. I'll put kilogram m over s squared m squared, that is. And then we are multiplying it by this s that came with the js, and then we're dividing this through by what we have as the denominator SI units. Now let's cancel out some SI units. Seconds and seconds will go. These seconds and these seconds will go. Meter and meter will go. kg and kg will go. Guess who survives? The m. That is why the SI unit right here is in meters. So that is the final answer. So if you are given the uncertainty in momentum to be 1.0 times 10 to the power minus 24 kilograms meter squared of an electron, its uncertainty in position will be 5.27 times 10 to the power minus 11. So you can tell that if you know one, the other one will drastically be below. The value is going to be so low. As you can tell, here it's 10 to the power minus 11, here is 10 to the power minus 24. So delta P is quite a very small value compared to delta X. In the previous example, here we were given delta X as 1 times 10 to the power minus 9. Here delta P is 10 to the power minus 26. So you cannot determine both of them at the same time. These 10 to the power minus 26 is quite small. It's very, very small. Okay. So knowing delta X, you will not know delta P. Oh, that's what Heisenberg uncertainty principle is saying here. That electrons behave like waves, and they're extremely light and small. Their wave-like nature makes it impossible to know both their position and their momentum precisely. The more precisely we know one quantity, which is position or momentum, the less likely we know the other.